My name is Pujanjali Shukla. Roll number 205047 is going to explain you the topic groups. So first, let us see the number system. There are many sets like set of natural number, set of whole number, set of integer, set of real number and set of complex number. So what is non-empty set? A set is non-empty when it contains at least one element. Now what is group? A non-empty set G with an operation O is said to be a group if it satisfies the following conditions. The first condition is the closure law. For every A comma B belongs to G, then A operation B belongs to G. Second, associative law. For every A comma B comma C belongs to G, then A operation B operation C is equals to A operation bracket B operation C. Now the third is existence of identity. For every A belongs to G, then there exists E that belongs to G such that A operation E is equals to E operation A, which is equals to A. Here A is known as the identity element. Now the fourth is existence of inverse. For every A belongs to G, then there exists an A inverse which also belongs to G such that A operation A inverse is equals to A inverse operation A is equals to E. Here A is known as the inverse of A. If G be a group with respect to operation O, then it is denoted by G, O is a group. Operation can be addition, subtraction, multiplication or division. Now what is abelian group? A group G, O group that is it satisfies that all four conditions is said to be abelian group if it satisfies commutative law. That is, for every A comma B belongs to G, then A operation B is equals to B operation A. Now what is semi-group? A non-empty set G with an operation O is said to be a semi-group if it satisfies the following condition. A non-empty set is said to be a semi-group if it satisfies the condition of closure law, that is if A comma B belongs to G, then A operation B also belongs to G. The second is the associative law. For every A comma B comma C belongs to G, then A operation B operation C is equals to A operation B operation C. Now what is trivial group? A non-empty set G which only satisfies one condition, that is the existence of identity, is said to be trivial group. Now what is order of a group? Number of elements in a group, that is G, O, is known as the order of a group. If number of elements in a group are finite, then it is known as finite group. Otherwise, it is known as a group of infinite order. Let us take a question that show that set of integer is an abelian group with respect to addition operation. Here the operation is addition. So integer, set of integers. So we know that I set of integer is I, 0, plus minus 1 plus minus 2 plus minus 3 plus minus 4 and so on, is set of integer, and we have to prove that I plus is abelian group. For abelian group we have to satisfy the 5 properties, that is the closure law, associative law, existence of identity, existence of inverse and commutative law. So let us prove the closure law. For every A comma B belongs to I, then if we add any two number of the integer group, we get that number which belongs to I. So closure law exists in I. Now associative law. For every A comma B comma C belongs to I, then A plus B plus C is equals to A B plus C. You can check any three numbers. If you add 2 and then add the third one, you always get the same. So it also exists in I. Associative law exists in I. Now existence of identity. For every A belongs to I, then there exists 0 that belongs to I, such that here 0 is the identity element. As you can see, if we add any number from 0, we get the same number, that is A plus 0 plus A, we get the same number. So here hence identity element exists in I. Here 0 is the identity. For addition, 0 is always the identity. Now existence of inverse. For all A belongs to I, then there exists A inverse such that A plus minus A is equals to minus A plus A is equals to 0. The inverse of A is minus A. As you can see, when we add these two numbers, we always get the identity, that is 0, which we have found here. Now existence of inverse also exists. Now we will prove the fifth property, commutative law. For every A comma B belongs to I, then A plus B is equals to B plus A. So here commutative law exists in I. Since it satisfies the 5 conditions, so hence integer with operation of addition is abelian group. Now the other question is that is set of integer abelian group with operation multiplication. We have done for addition. Now we will see is it abelian group with multiplication. So we know a set of integer I is equals to 0, plus minus 1, plus minus 2, plus minus 3 and so on. And now we want to check I is abelian group or not with respect to multiplication. So first of all, closure law. For every A comma B belongs to I, then A multiply by B also belongs to I. So closure law exists in I. Associative law, for every A comma B comma C belongs to I, then A dot B dot C is equals to A dot B dot C. So associative law also exists in I. Now existence of identity. For every A belongs to I, then there exists one that also belongs to I. You can see one is belonging to an integer set. So A dot 1 is equals to 1 dot A. We get the same element. When we multiply any element with 1, we get the same element. So existence of identity exists. Now existence of inverse. Since inverse of each element of I does not exist except 1 and minus 1. For each and every element, inverse is not existing. So hence inverse does not exist in I. And since one of the property is not existing, hence I with operation multiplication is not a group, that is I with operation multiplication is not abelian group. Now order of an element. If G be a group and A belongs to G, then order of A is least positive integer n such that A to the power n is equals to E, where E is the identity of G. It is denoted by order of A, which is we can write as O bracket A, order of A. Note, if order of A is equals to n and A to the power m is equals to E, then m is greater than or equals to n. The order of an element A is said to be 0 if no positive integral power of A is identity. Now let us see a question. Find the order of every element in multiplicative group. G is 1, minus 1, I and minus I. So given that G is given is multiplicative group. So for multiplicative group, what is the identity? E is equals to 1. Identity is 1. So now we will check for each and every element I, minus 1, I and minus I. For 1 to the power 1, it is equals to I, which is the identity. So order of 1 is I, 1. Order of 1 is 1. Now for minus 1 to the power 2 gives us 1, which is the identity. So order of minus 1 is 2. For I, we can see when we I to the power 1, it is not giving us 1, so it is not the identity. We have checked for I square, I cube and I4. When we checked for I4, we get 1, which is the identity. So order of I is 4. Same for I minus to the power 4 gives us the identity. So order of I minus is 4. Now a theorem. If an element A is order of n, then A to the power m is equals to E if m is a multiple of n. So here prove, let G be a group. We have let that G is a group and order of A is n, which is given. Now n will be the least positive integer such that A to the power n is equals to E. We marked as equation 1. Now what we have to prove is that A to the power m is equals to E if m is a multiple of n. That is m is equals to kn, where k belongs to an positive integer. Now let A to the power m is equals to E, then we have to prove m is a multiple of n, that is m is equals to k dot n. Let m is not multiple of n. Here we put the contradiction that m is not a multiple of n. Then m is equals to k dot n plus r. Here r will be less than 0 or greater than 0 or less than n. A to the power m is equals to e. So a k plus k, a to the power kn plus r is equals to e. We can write as k to the power kn dot a to the power r is equals to e. Here it follow associative law since it is a, so a to the power n bracket k dot a to the power r is equals to e. Here a to the power n, we know it gives e, so e to the power k dot a to the power r is equals to e. Now any identity multiplying to any power will give us e, so e to the power e into a to the power r is equals to e, and when we multiply any element with its identity we always get that element, so a to the power r is equals to e, which is not possible. On a order of a belongs is equals to n, and here r is greater than n, hence our supposition m is not multiple of n is wrong, hence m is a multiple of n. Now it's conversely. Now we will let m is multiple of n, then we have to show that a to the power n is equals to e. So since m is a multiple of n, then m is equals to kn, where k belongs to a positive integer. Now a to the power n is equals to a to the power kn. We can write as a to the power nk, which can be written as e to the power k. So a to the power m is equals to e. We have proved this also. Now what is subgroup? If G be a group with operation O, then a non-empty subset H of G is said to be a subgroup of G if it is also a group with respect to same operation defined on G, that is operation O. If G be a group, then it must have two subgroup, namely G and I, known as improper subgroup, and the other subgroup of G are known as proper subgroup.